So we'll start the recording. What I'm going to do is I'm just going to do a quick run through of essentially something that should be almost identical to what you'll be doing, what you need to do for your first program. So what I'll do here, okay. I'm going to have a makeup idea here where we're going back 150, 200 years. 150, let's see, 180 years, 170, 180 years, the Pony Express. They developed a system for delivering mail around the country. But Pony Express riders didn't ride to every town. So if you had to send a letter, say, to somebody in someplace in Wyoming, you probably sent it only to Cheyenne, and then they would have to get to Cheyenne somehow to get to it. So what you had was a network of you had a network of cities. And they might have been connected in different ways to allow people to send mail from one place to another. And yeah, it's not going to be very interesting to do that because and so this is on the fly. Let's see how we can do it. So I can get to that one two different ways. This one requires 3 steps. We'll have one more city here. So let's say that this one's Topeka, Kansas. Topeka, Kansas, top. We'll say this one is Salt Lake City. This one, we'll say this one is Durango, Texas, or Durango, Colorado. From Topeka, we might go to Denver. We might also go to, I'm trying to remember where Topeka is relative to everything else. We might go to Cheyenne from there. And then we might, from Denver, we might also go to, thinking of the map here, how we might do it, like Flagstaff. It's not Florida, we'll just call it Flagstaff. And then from there, we might also go to Phoenix. So we have this sense of routes. You know, this is Pony Express routes. And the question is, for example, if I'm in Topeka and I want to send something to someone in Phoenix, what do I have to do? Well, I've got 2 choices. And you know, the question is there a fast way and a slow way, or is there only a slow way? So in this case, I can go through Denver to I know I'm going to mess that up, but Flagstaff down to Phoenix, or I can go from Topeka. We'll do 2 in blue. See if they have a good green on the other one here, because we've got at least a couple of different routes. Or I can go from Denver to Salt Lake City to Phoenix. Or I don't even have to do that. I can go through Cheyenne to Denver. Or you get the idea. I've got a bunch of different ways to get from Topeka. I want to send something there to somebody in Phoenix, or somebody in Salt Lake City, or somebody someplace else. So that's the idea. My Pony Express riders only go certain ways. The question is, how many stops is my Pony Express? How many different Pony Express riders, or how many stops? How many intervening cities? So that's the idea. So we're going to do this very quickly here. So our idea is Pony Express. Make sure I'm sharing my screen. I think I forgot to share my screen on Discord. I'm in Discord, but I think I forgot to share my screen. I don't think there's, oh, there's somebody else there. So we'll do that. Sorry, I forgot to share my screen. Now I'm doing that. So now you should be able to see that. My apologies also, I have not found a way to have my camera shared between my recording and my broadcast. So we have to do this. So this is Pony Express. Nope, wrong place. Pony Express. So how many riders are intervening cities? So what we're saying here is that we have riders from or between cities. Yeah. So between cities. So basically we'll go here. I've got between, and I've got Topeka and Cheyenne. I've got between Topeka and Denver. I've got between Cheyenne and Denver. I've got between Cheyenne and Durango. I've got between, oops, almost spelled it out, between Denver and Flagstaff. I've got between Denver and Salt Lake City. I've got between Durango and Salt Lake City. As you can see, if you're looking on Discord, you can't see the graph I drew on the board, but it's essentially just I've got circles labeled with TOP, CHE, DEN, DUR, FLA, SLC, and Phoenix is the last one. So here we've got all the Durango ones. We've got we could duplicate and say Durango to Cheyenne, Cheyenne to Durango, but we won't worry about that. We'll just say that it's one way right now because it doesn't affect our problem per se. It just is how many possible ways we can do things, and we might end up with loops, and we don't, all kinds of stuff like that. Finally, we've got between Flagstaff and Phoenix, and between Salt Lake City and Phoenix. So we're saying that this is nominally the routes that we have or the riders that we have for our Pony Express routes. So actually they used to go through places like Fort Huachuca and, not Taos, some of the places in New Mexico like Santa Fe and Albuquerque. I mean, the riders basically went all over the West, but they just went to cities. They didn't go out and stop at somebody's house and say, "Hey, Bob, I got a message for you." It wasn't quite that way. So now the question is, how can we compute the routes between cities? Note, we haven't done the reverse routes here But for the problem for your programming assignment, you don't have any reverse routes. You're just saying we've got these, planes from one place to another. How do we do stuff like that? So here we go. Not 4. So what we would want would be something that would say that there is a route from A to B with, X riders if there is a between from A to B, and that's what the comma is, X riders is 1. So what that's telling us is that I have a way to get from one place to another if this is the number of riders that will be involved. If there is a between A and B, that means that X riders is going to be 1. So a rider would have one route. They didn't say, okay, well, I'm going to go from Topeka to Cheyenne, and then I'm going to ride another 3 or 4 days to Durango. No, they didn't do that. They had their route. They would drop it off, and then the guy who rode the other route would come in and pick it up and carry it some of the rest of the way. So we now need to get that part. So here we'd say a route from A to B with X riders exists if there is a route from A to somebody else anywhere, C, with Y riders. And once I get to C, I can get to B with X riders. Pardon. If I can get to B, then what I have to do is set X riders is Y riders plus 1. So this is saying if I can ride if I want to get to Salt Lake City, I can do that if there's some place in between that I have a route to. So this would be A to C with 1 rider. And there's something between here. I can add that leg, and that makes something with 2 riders that will get me from Topeka to Salt Lake City. So we use the inference engine to build our route, and that's really all that we're doing here. Once I get to Salt Lake City, I can build the route to Phoenix. So once I get to Flagstaff, I can build the route to Phoenix. So this becomes our means of doing stuff. So we'll save the buffer. Save the buffer. It's not quite like saving the whale, but almost. And over here we can consult it. Luckily, all green. All green means that I don't have any typos in it. It does not mean the logic works. It just means no typos. We're okay. So here I can say, okay, do I have a route from Topeka to Phoenix? And how many riders does it have? So it's a query. It's just, I'm just asking the question, how many different ways can I get from Topeka to Phoenix? So if Bob is not running his route, do I have a backup route to take? So we bring this in. So I can do it with 3 riders. I can do it with 3 riders. I can do it with 4 riders. I can do it with 4 riders. I can do it with 4 riders. So I've got 3 ways to do it with 4 riders. I got into an infinite loop here. I must have put things in a weird order here. Okay, so what we need to do is, oh, this one. Let's run. We'll just interrupt. And I don't remember H. I want to abort. Yeah, I got into an infinite loop there, and that's not a good thing to do. And it's probably because of the order I have things in here. So let me change my order just a little bit. So we'll put that in here. I hope I copied it. I should have. So I should be able to paste it. There we go. So now if I have, we want to make sure that we stop with the, there's got to be the first route. Otherwise, there's a lot to search through, and that makes life difficult. So that's kind of the thing to do. We can add stuff in here by just saying, tab, quote, let's see, and then right. So these are always true. So if the rest of it is true, we'll do these things. We will do these things only when the other ones are true, and we'll write C. So C will tell us something like, how are you going? What's making this thing happen? So we'll save it. We'll reconsult or reload. And down in here, all we have to do again is we can go route from Topeka to Phoenix with riders, period. So that gives me one. What it's saying is I start in Topeka, I can go to Denver and then Flagstaff, and I'll have 3 different routes. And then semicolon will give us another one. Cheyenne, Denver, Flagstaff with 4 riders. Denver, Salt Lake City with 3 riders. Cheyenne, Denver, Salt Lake City with 3 riders. Cheyenne, Durango, Salt Lake City with 4 riders, etc. And that was the end of it. So there are only that many ways to go. But that's the idea in terms of what we're trying to do. We don't want to get too complicated, because the more complicated we try and make this, this is not a procedural, functional, imperative language of any sort. This is a logic language. As a result, these are not really function calls. What these are, each one of these is something that is true or false. And because I have commas between them, that means everything that's true will be the thing that's reported out. So it's not like I'm calling anything here. In fact, these two, as I said, only happen when the other parts are true. It's the only time that I'll actually get those. So that's the idea of what we're doing, what you're doing in your first program. Simplicity. As you can see here, I've got more betweens than you have flights. But if you have more than about 15 lines in your code, it's too much. So just keep that in mind, that you're not trying to reinvent everything. This is really very simple. I don't have to define, I don't have to say, well, city, Topeka's a city. I'm not using cities here. It'll get a name, because what it's trying to do is it's trying to match here. What are C and D? Do I have something that makes C and D true? Well, I do. So it looks and it says, okay, SLC in Phoenix makes this true. And it'll try and build stuff that way. So it builds the route as it goes through and tries to do all the resolution on all this. So it's building a search tree, going through the graph I have here. It's building that search tree and trying to figure out, hey, what's going on? How can I make all of this true? Of course, for queries, I could just have it list everything. So here I could have route, A, B, riders, and it would give me, okay, I can go from Topeka to Cheyenne with 1, and it'll just list everybody.
all the distance 1, all the distance 2, some of the distance 3, and it just lists and lists. So those are all the possible routes because I haven't made these go backwards yet. So we've got to be real careful going backwards because that can lead to infinite recursion because I'm going back and forth and back and forth and back and forth. So we want to stop that kind of thing. And it's beyond really what we're trying to do in the homework. We're just trying to show that we can set up predicates or predicates here with our rules, and we have our propositions at the top, and we can combine those to build other things. And do a little math on the side. So that was the first programming assignment in a different kind of look. This is our Pony Express riders versus flights, and that's really about the only logical difference here. Other than also here I always have one rider, pardon me. And if we're looking at flights, if I have a direct flight between, say, Topeka and Denver, then I don't have any stops. I don't have any layovers. So in one case in your programming assignment, you are always working with one fewer than we have here. So you would initialize with big 0. So that's really about the only difference here. I've started grading them. I have not completed yet, but I wanted to do that as a means of exploring really what's going on and trying not to get to the point where you shouldn't be feeling overwhelmed. If you feel like you have to spend 4 or 5 hours trying to research this, it's way too much. Way too much. So writing stuff out is not really complicated. Just use a write for each individual thing as opposed to like C out where you can list a whole bunch of things, or Java where you can have a system out print line with a string concatenated with something else, very simplistic input and output here. So we have to be simple with the whole thing. Questions? If you haven't finished the first programming assignment, hopefully this will have helped. And if you have finished it and this didn't look familiar, you'll have an opportunity to submit again. So, all right, so let's go ahead and press on. That took a little longer than I anticipated, but not too much. Because we can zip through this because you guys are propositional experts now. And Boolean algebra experts, undoubtedly. So what you see here is I've got a whole bunch of things here. The key word here is predicate. That's what we're talking about today. And you may notice something here. We've got variables, the dreaded variable. So we're going to start with a quick review. We'll look into predicates. We'll talk about... Actually, I need to get rid of the equivalences here. I don't have any equivalences in this one. We'll talk about equivalences on Thursday. So, review. Last time, propositions, or last week, propositions. I've got some property in Florida if you want it. It's a little wet. There's a lot of property in Florida wet right now in the Great Bend area. I lived in Florida for a little while. My parents lived there for almost 30 years, so, or almost 40 years. Dad's not there right now. Mom passed, but Dad's not there anymore. A proposition is a true-false statement. It has to be true-false. It has to be objective. It can't be, oh, it's hot in here. Is for me, I'm kind of dancing around up here, drawing on the board and stuff like that. For you guys, it might be, man, it's kind of cold in here. I'm going to bring a coat next time. So that is a subjective thing. Is that correct? That's a question, which would not be a proposition. So we have all the different things that are not a question, command, opinion, statement, nothing with a variable x is greater than 3. Maybe, maybe not. I can't tell if it's true. You haven't told me what x is. And if I'm combining two of them together, that means I've got two propositions. X is equal to 3 and x is equal, and you haven't told me that the x's are the same. So anyway, We can combine them using operators or operations. We have the not, we have the and, we have or, XOR. Those are probably the most unusual ones. We have some others that we use in Boolean algebra, with NAND and NOR. Anybody in here have 2810 yet? When you take 2810, they'll probably talk about NANDs and NORs. You can build any Boolean algebra circuit using all NANDs or all NORs. So one of the nice things when Radio Shack actually was selling chips, you could design almost anything, go in and buy a bunch of, I can't even remember the chip numbers because it's been 30 years or 40 years since I did that, but and I didn't buy them. They provided them for me in my physics lab, but anyway, that's the kind of thing that we can do. We also have some other things. We have implication or conditional statements. That's the if P then Q, or if some proposition then the other proposition. It is not that P will change the value of Q. This is just another operator. So don't get wrapped up in the English language for it. Just say, oh, it's some symbol, and I know the truth table for it. Same thing with the biconditional. It's a symbol. You know the truth table for it. So they have a truth table. Basically, when you have a large expression, just use the truth table to do it. Here's an example. Normally what we would do is we would list our input variable values. So here, P, Q, and R are our propositions. Are not variables, but our propositions. We list all the possible propositional values and the combinations. So if I have 3 of them, I'm going to have 8 rows. 4 of them, 16. 5 of them, 32. 6 of them, 64. And by that point, my arm will be so sore I won't be able to write anything. So, but here I've got 3 of them. We then normally will break this apart into any parenthetical expressions. So that's what I've done here. I've got parenthetical expressions, and I just do a truth table for them based on their input. So I look at P and R, and I say, okay, P and R. P is false for the first 4. The first 4 have to be false. P is true for the second 4. So the only time it's true is when R is also true. So I have 4 falses and then false, true, false. So yes.
I was just looking at Q and R, and should there only just be 2 truths in that column? Or it says there's 3, but go over to Q.
There probably should be 2, and I just have a typo in there. Yeah, I should have a true here and here. So only it's more like it's more like the last value. So this one is actually false. Thank you. I've had that mistake in my slide for at least a week. Actually, it's been there for a little while. But yeah, that mistake wasn't there. So yeah, sometimes it gets difficult to see things. So then if you're trying to do the or, then you would combine these. I have the first part should be the P and R is all false, and I've only got 1 true here, so with an or that would be true. And down here, these first 3 are false, but I've got a true here and a true here. So both of them are true there, so we end up with our final value. Yeah, so I would have got let's see, out of 8 times, let's see, 1, 2, 3. So out of 24 possible points, I would have missed at least 1. So, happens. Boolean algebra, our other part of our review, this is algebra with only 2 possible outcomes. 1 plus 1 is 1. So it's only got those as the possible results. There is no other possible result there. So I can't have a 1, 0 because I've only got a 0 and 1 as a possible output. Our operations are and or and not, but we call them sometimes multiplication, addition, and complement. So we can either talk about them as logical operations or as algebraic operations. And if you recall, we do have the properties such as distributive law, commutative law, all those different kinds of things that we can use in order to, and the identity laws, we can use all of them to simplify or change the representation of the function to get the same algebraic output. We use these to model logic gates. This is what we're doing in the second programming assignment. The circuit that I've given you there is actually a 2-bit adder. So if you can add 2 bits together, then you can get the result. For example, I've got 0, 0, 0, 1, 1, 0, 1, 1. I'm going to have a sum and a carry output. So 0, 0, my sum is, and my carry is a 0, 1. My sum is 1 with a 0 carry. My sum is 1 with a 0 carry. And then here I should have a 0 by 1 carry out. So in binary math, that's what we get. And the circuit that I've given you actually does this. So you should be able to get, oh, this is just 1 bit. We actually have a 2-bit. This is a 1-bit adder. For a 2-bit, I'd have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, and I have 16 others, or 12 others to fill in. But you should be able to query the circuit and get a complete truth table. So I also gave you, you're going to have to look at how you call it. I gave you, I can't remember the name of it, it's P something or other. It's a print for the values. What you want to do, this would be A0, A1, B1, B0. The 0th bits and the first bits. When you call it, you probably want to call it print. I think it's print row. It's a row of the truth table. You would call it with A0. To get it to print the way that we would normally expect, you would call it with A1, A2, B1, B2, B2. We don't have any subscripts here. Sum 1, sum 2, and a carry. And that would be the way that you would, pardon me, sum 1 and sum 0. So when you call it, those are the values that you would be using in order to get it to look like what we would expect with, I'm adding 0, 0 to 1, 0, I should get a 1, 0. Or I'm adding 0, 1 to 1, 1, I should get a 0, 0, and a 1 as an output. So as a carry. So that's the idea with what's going on with the function, the code that I provided you, the rule that will print the values there. It is equivalent to propositional logic. Because we're only limiting our values to 0 and 1, our multiplication ends up being similar to an AND. Our addition is equivalent to an OR, and then our complement is the same as a NOT operation at that point. But we can go a little bit further in terms of implementing things like an adder. And when you take 2810, you'll probably implement a 32-bit ripple carry adder. So doing the same sort of thing. Operators we write differently. So our AND or multiplicative operator, if it's not ambiguous, we just leave there's no operator between them. Otherwise, we put a dot. I don't know why they decided on a dot. Keyboards at the time. Well, you could actually do a little roll. Remember, most of this was done in the 1940s and 50s and 60s, where you had IBM Selectric typewriters, and you could kind of roll it halfway between and put a period there, and then roll it back down and start typing some more. I'm trying to remember what the key was. There was a key that would change the location of the carriage so that you could. You know, I did take typing in high school. It was big. Now it's keyboarding. It was typing in the 1970s. Or A plus Y. We don't have any alternative here in terms of Boolean algebra. As you know, for our propositional logic, it's normally a vertical line. It's also a vertical line in bitwise operations in computer science, most of the programming languages that we have. And then finally, are not. We're no longer using the minus sign with the little hang tooth or buck tooth piece on the end of it. Instead, we're using either a line over the top of the variables or expressions, or a apostrophe, in which case we'd have to use parentheses to group things together. All right. Finally, we're ready to start this week's material. I know you've been awaiting this. It's the dreaded predicate. It's kind of like the comfy chair in Monty Python when they did nobody expects the Spanish Inquisition. They had the comfy chairs. Never mind. Does anybody ever watch the old BBC stuff anymore? My brother was big into Blackadder, but I remember my parents would even watch Monty Python on PBS. We had 4 stations we could pick up. It was great. But we've limited propositions so far to statements that are objectively true or false. There's no additional information that has to be brought in. We can't have variables in there. So that was our limitation. We had to have a statement that said the sky is blue. The sun is up here in Utah. That would be kind of implied in our statement. It's raining. It's windy with the wind above 10 miles per hour. So we would have objectively true statements that we would be able to say something is either true or false. But oftentimes, because we are talking about more than one thing most of the time, we like to talk about the properties of things in terms of sets of things. 50%, what is it? It's something like 90% of the population got the COVID vaccine. 4% of the population is AB positive. AB negative. So those are the kinds of things that we do. We have sets of people when we create statistics on those. We have sets of computers. How many of the computers did you upgrade to Windows 11 Pro Service Pack, or whatever the build number, I guess, is the appropriate way to say it now. So we have a set of things, and in your business or in the place you work or in government, we deal with sets of things, and we talk about what's true about either individuals within the set or about things within the set as an entirety. And the way we do that is by using a predicate. Basically, a predicate is a proposition where instead of saying that computer has Windows 11, we talk about the predicate. This computer has Windows 11 installed is true or false for, and then we would list all the computers in here by some identifier, some means of identifying them. And that would be our predicate. Our predicate would be has Windows 11 installed, and then the things that we would have for our set we would limit to machines in a particular room or computers in the entire world. You can actually do, there are people who keep statistics. I don't know how accurate the specific statistics are, but they keep statistics about all the computers in the world and how many of them have different operating systems installed on. I believe it's Steam does that. They collect data about the
the systems that connect to Steam in order to play games, and that's used as a metric to talk about how many people are running Windows 95 versus how many people are running Windows 11. And yes, Windows 95 is still out there, ready to bite you when you least expect it. We write it as a capital letter typically to indicate that it's a predicate as opposed to a proposition. And then in parentheses, we put one or more variables that are used within the predicate. You know, for example, you could have a predicate is related to, and we could have P would be the predicate is related to X is related to Y, and then in the parentheses we'd have X and Y, and then if you have you could have people, you could have businesses. You know, if we could define what the relation was, then we could say P of X, Y is either true or false, depending on the values of X and Y. And that's the key thing here. It's either true or false, but only when we give a value to the variable or variables that are in here. If any of the variables is not defined, then it has no true or false value. It's not yet determined at that point. It's simply saying that if you can tell me all these different things from the sets that they come from, then I can tell you it's either true or false. Now, give me the computer. Yes, this one is Windows 11. Windows 11, a pre-release, a preview version. We get the values from that set. The set could be anything. I've listed here integers. That's everybody's favorite. Oh, yeah, the set of integers. That's the one we like. Or automobiles, marsupials, you know, citrus fruits, whatever we want, the predicate's going to determine, once it has a value from the set, whether or not we have a true or false statement. So some examples here. Let our proposition be X has an AMD processor in their computer. And this could be in any of their computers. We would write this P of X. So X. So now we have to say what? Where does X come from? Let's go down to kitty care, find all the kids that have computers, you know, the 2 and 3 year olds. How many 2 and 3 year olds have computers? Not very many. So we have to define, well, where is X coming from? What set are we drawing these things from? Because that can determine the truth or falseness of some particular thing. So we have to define our set before we do anything else. As an example, we could use people in this class. So X would be a person in this class. Let X be an element of the people in this class. In other words, one of the people in this class. Then the proposition P of X is the proposition X has an AMD processor in their computer. Anybody other than me have AMD? I mean, my work computer, I'm stuck with what they buy me, and you know, it's hard to get a really good laptop that the government will buy with an AMD Ryzen processor in it. But my home builds, I've built only my last 2 computers, and you know they're both AMD. One of them is a good space heater, because it's an older processor. My current one is not nearly as bad, and I've been very happy with it for the last 2 years. We could have another predicate. We could say X is over 6 feet tall. Anybody in here over 6 feet tall? Not me. Yeah. So that would be another predicate that we could apply. X weighs less than 100 pounds. Could be true for, I mean, once again, I'm picking all these things that don't apply to me. But our predicates are simply expressions, and we say we can apply that to a specific individual from a set, or a specific element of a set. You know, if we're talking about automobiles, you know, can drive faster than 200 miles per hour. Anybody own a Bugatti Veyron? I'd love to try one sometime. I don't know that I'd want to own it. I'd be afraid of somebody. I had somebody at Walmart that hit my car with a cart and left some beautiful scratches on the back end. And I'm sure with my Bugatti, I would be prime if I could afford one to begin with. I wouldn't have to worry about it. I wouldn't be going to Walmart, but anyway.
Really quick question.
Yeah.
On that, with the first one, like with the people in the class, would it have to, all of us have to have an AMD processor for that to be true, or would it just, is it?
It would take on either true or false values once we said, okay, do you have an AMD processor? Is it false? Point to me. You have a, yeah, I do. So it would be true. So it's only once we get one element from the set and we can say it's true for that element. So here, there's nothing that says that we're talking about the entire set of people. We're simply saying we're going to talk about things from this set and say that it's either true or false.
So, but good lead into our topic that we're getting to in just a second. We can use our operators here. Since I'm the only one with an AMD processors, then that means has an AMD processor is true, over 6 feet tall, false. So it would be a false expression. So we have the ability, just like we do with propositions, the sky is blue and all birds fly. Sky is blue, true. All birds fly. Ostriches, emus. Pardon me?
Only to throw them.
So if you throw them hard enough, they don't really fly, they glide. You know, that's like saying a flying squirrel flies. They don't really fly, they just climb up really high, jump off, and humans, do humans fly? Well, if you give them some really neat suits, they can glide a different away, or if they put an engine, isn't there one of those suits that they put a jet engine on? I thought there was. Have you ever seen any of the videos where they get to the top of the mountain and they jump off and they glide down and they have the helmet cams? That's something I really, it's neat to look at the video, but no, I can live without it. So we have our operators, we have the ability to combine them. If we have an expression like that, it's important to know that the x in both of the predicates must be the same x. Okay, what if we do want to make, you were talking about the sets. What if we do want to make statements about the set as a whole? This is the kind of thing that we're generalizing in this case. We could do something like X has an element of has an AMD computer. We've talked about that. We can say that if X is a person in this class, the predicate P of X is true for all people in this class. Well, that would be another form of the expression. But as we know, you guys you're just Intel lovers. That's all. That's okay. My brother gets his retirement stuff from Intel, so you can continue to fund him. But the point would be that we can have the expression that P of X is true for everybody in the class, but at that point, it's going to once again be a true or false statement. So when we make statements about the set, we still have to resolve to the statement being either true or false. The way we do that is with a quantifier. Quantifiers are things that say, given a set, something either is an expression about all the things in the set, at least one thing in the set, or exactly one thing in the set. Those are the three quantifiers that we have. So the quantifier allows us to talk about the set with regard to a specific predicate. For everybody in this class, everybody is over the age of 3. So the predicate would be Everybody is over the age of 3. And the set would be people in this class. And then we could say, for everyone in this class, for every X person in this class, X is older than 3. And that, I hope, would be a true statement, unless you are a clone that has been, oh, well, we haven't gotten to that technology yet. We'll talk about that later, maybe. For example, for all, and what I've just been talking about is all the elements of the set, everybody in this class. And to do that, we have to use what's called the universal quantifier. What this is saying, how many remember we're going to get into sets in the next couple of weeks, but how many of you remember the idea of sets? A set is a description of items that come from some universe. So if I say automobiles, I could be talking about all the universe of automobiles, the universe of fruit, the universe of people, the universe of people in this class. So I define a universe, the set that I'm drawing things from. So the universe is saying all, universal, all of the things within our set. Our set is our universe. Can I say something about everything in the set? In this case, we have a specific symbol for that. Anybody ever see the upside down A? It basically says, in math, if you've probably seen it in algebra, perhaps calculus, if you've had calculus up to this point, it's basically a for every. This is the normal math way of saying this is, for every X, P of X is true. That would be the way that we would read this. This would be the only part that you'd see. Is the upside down A, the X, the capital P, and the parentheses of the X inside. That would be the way that we would write the actual expression. But it's the same as saying P of X is true for everything in our set X. Every X that is an element of the set. Yeah, and which is the people in our class in this case, and probably not everybody has a name. You guys really need to come over to the light, escape the dark side of the force and come to the light. We can also talk about whether the predicates are true for at least one value. As you can figure out, it's not going to be an upside down A. We have a different symbol for that. So when I was putting this together, I ran out of room because otherwise I could put the font down to about 10. Or, it'd be about like that. And you guys, if with a pair of binoculars, you could probably read the slide. We don't want to do that. So we're going to have more fun here, and we're going to talk about something that says that one exists, or at least one. So we're talking about the existence of something. There is an element X such that it makes the predicate true. Has an AMD processor in their computer. There's got to be one. Might be more. It could be everybody. Uses a computer occasionally that has an Intel processor in it. How many of you fit that? Actually, I do more than occasionally. I have that. I carry this thing with me. It's almost like a ball and chain. But Intel processor, the most common processor out there. So we would be able to say that that's probably going to be true. There should be at least one person. But there should be at least one that uses an AMD too. I mean, we got to be fair here. But this is called the existential quantifier because existential is based on the idea of existence. So it has no further meaning than that. So when somebody says, yeah, I was doing some existential meditation and trying to figure out they're talking about just existence or whether something exists or not. Once again, we have a special symbol, a backwards E. The word we use is there exists. There exists an X such that P of X is true. The predicate is true with X as the value. At least one, maybe more, makes P of X true. Now, the point really here is that no matter what we do, let me see, pull out my pen here. See if I haven't. This just like the one with the other operator is true or false. There's nothing special about it. It's just saying there's something in my set that makes it true. Well, that's going to be true or false. Everything in my set makes this true. It's going to be true or false. And as you can imagine, with more room left on my slide, there's got to be something else. Well, the other one is uniqueness. Anybody in here ever see Highlander? The movie Highlander? Oh, man. I'm getting too old. You guys can't relate to the 1980s movies or the 1990s TV show with immortals running around, nearly immortals running around cutting each other's heads off. Man, where is the death and destruction in our society these days? It's supposed to be on TV. Anyway, our final one is uniqueness. The line is, there is only one, would be the way that we would have to read it, or there exists uniquely. The expression from Highlander was, there can be only one, but that's kind of the idea. That's why before they cut their heads off, sorry guy, there can be only one. Actually, they were really more dramatic about it. There can be only one. But here we're talking about kind of the same thing, that there is only one. There is, out of the population of the United States, there exists only one president. Yeah, we only have one president. They're not two. They're previous presidents, but they're not currently president. So we only have one. So that would be an example of this. The way we write it is we have our backwards Z's, the existence, and we're emphatic about it. There's only one. So the exclamation point after says, there exists an X that is unique. There is only one. How many values of integers are there? Wait, let's see. Let's do it this way. There exists. Oh, shoot. You wrote so nicely before. Now you're not writing at all. Give me a break here. Then, okay. Not writing. Okay, let's see if we can get it to do something. Okay, let's do it this way. X is the set of people in the United States. Let P be the predicate. P is true if X has donated blood. So then there are true or false statements that we can have. For every X, element of the set of X, P of X. True or false? Is everybody in here donated blood? So it's false. For every X, and I promise you it will always be false. There will always be people who have not donated blood. That's okay. It's just a true or false statement. So the universal quantifier here would normally be, for every X element of set, P of X, this would normally be false. I would expect it to be false because you normally don't take blood donations from people under the age of 16, under the age of 18 with their own permission, under the age of 16, or down to the age of 16 with their parents' permission. There exists X, element of set of X, such that P of X is true. I've donated, not as often as I used to, but I still donate periodically. Yeah, that's true. There's at least one person in the country that's donated blood. Not necessarily me, though I have. There could be more. Is there more than one? Yeah. Anybody in here ever go to a blood drive? Yeah. How many people are there? Usually more than two. So So if we have this one, there exists a unique person. So if you ever get in an accident, Bob's the one who gives you blood. Is there a singular Bob? No, there's not. One person trying to give enough blood for 330 million or 350 or however many million we have. It doesn't work that way. That person would be forever hooked up to tubes and probably would not have much of a life. So this one's false. The top one and the bottom one are false. The one in the middle is true. There exists at least one, in fact, but again, they're not. There's not more than one. So propositions are true or false on their own. Predicates are true once a value is given, and then our quantified predicates represent properties of the entire set. You know, kind of giving us a feel for something like the proposition. Let's Q be the proposition that X has voted. If you were to look at the population of the United States, everybody in the United States has voted. We could even limit it. People in the United States over the age of 21. Because I don't know, if you're under 20, if you're under 18, if you're 19 right now, you didn't get to vote in the presidential election. So let's say 21. Everybody over the age of 21 has voted in an election in the United States. True or false? False. It's just a predicate. It'll have a true or false value once it's quantified. There exist people in the United States that have voted in an election. There exists people in the United. There exists a unique person in the United States that has voted. Nobody else has voted. I don't know. In Chicago, sorry, I grew up in Illinois, so Chicago was notorious for the graveyard vote. Vote early and often was the slogan. Going 8 o'clock at one precinct, 9 o'clock at another, take a break, go to 10 o'clock, 10:30 to another. Yeah, early and often. That was the Chicago way. That's why a certain unnamed party has had control of the city for my entire lifetime. All right. The set can make a difference. The things that we have make a difference. For every x element of the set of real numbers, x squared is greater than or equal to x. How could we determine the truth or falseness of this? Try out some values. That's the easiest way to do it. I mean, there are certain values that you normally try no matter what you do. So I recommend anytime you're faced with something like this, look at the set, what makes the set have particular properties, and then choose values that are kind of boundary values. For example, let's try 1. X greater than or equal to 1. 1 is kind of a boundary value here. Anything greater than x squared is getting really big. At 1, x squared is going to be 1. So it'll be equal. So at x squared is equal to. So 1 is a boundary value. And in fact, for most numeric problems, 1 will be a value that you'll probably want to try out. How about 0? Or less than 0? Less than or equal to 0. When x is 0, what do we get? X squared is 0. So they're equal. -1. 1 squared. -1 squared is... Okay, I realize that as a math course, asking you math questions can be difficult. X squared, when x is -1, is 1. 1 is bigger than -1. -2. -2 squared is 4. So is this true or false? Okay. I've led you down a primrose path here. What have we not tried? What's our set? The set of, what makes a real number special? My kids always had trouble going back and forth between rationals and reals. Rationals where you have one number, one integer divided by another integer. Real numbers have no such restriction. But we often think of them in fractional terms. So why don't we try another range? Anything between, does the values between these two have it, do they have any special properties? If I have 10 pieces of fruit and I say, all right, I'm going to multiply by 0.5, am I going to get more or less? Less. How about if I multiply 0.5 times 0.5? That would be 0.5 squared. Is that going to be bigger or smaller? Smaller. So the idea here is that for the numbers x, the values of x between 0 and 1, if I square them, what's happening to them? They get smaller. So is this a true or false predicate? A quantified predicate. It's false. Not true. How about this one? If x comes from a set of integers, x squared is greater than or equal to x. It's going to be true all the time. Because we already showed for 1, 0, and -1. And it just gets worse for -2 and whatever. I mean, it gets bigger, more positive. And for the positive values greater than 1, we see the same thing. So this one is always true. What if it's x cubed? Why not? If we take the negative number and we say like -2 cubed would be -8, is -8 greater than or equal to -2? Nope. So we found a counterexample. It's one of the proof methods that we use for things is we'll find proof by contradiction. This is false for the cube because a single negative number can be an example where it's false. Now, if it said there exists, then we'd have to say, well, it's true. There are some that counter it, but there's at least one element that will make it true. So we can find an element where 0 makes it true, 1 makes it true. We can find more than 1. And for the uniqueness one, we found more than 1 that makes it true, so that would be a false one. That would be a false predicate. So let me see if I can get my pen to work. It's spotty here. I don't know why. So if I have, thank you, they're just x, element of a set of integers, such that x cubed is greater than or equal. No, that didn't work. Come on. X cubed is greater than or equal to. We might as well do x squared. Now see that x squared is greater. I don't know why my hand must be causing issues here. My tablets become more sensitive over time. And they don't. Unfortunately, I can't use this one's a tablet, but I can't hook up to it for my laptop. So that makes it more painful. And it's not going to cooperate today. Okay, so we won't worry about this. We talked about them. Just understand that the quantifier and the set that you're taking values from is are going to make a difference on the truth or falseness of what's going on. Program 2, we're looking at a circuit. This one happens to be a half adder in this case. This would be something that only does 2 bits, or actually no, this is a full adder. So with no carry in though. That's what makes it a half adder. Anybody ever watched The Black Adder? I've only seen a couple of episodes of it. It's anybody ever see Mr. Bean? Yeah, well, he did The Black Adder, so Rowan Atkinson has a very pretty good sense of humor. So, but here the key thing for a program 2, what are we doing? We're simulating a logic circuit with ands, ors, not gates in it. The key thing to keep in mind here is that what we're trying to do is we have to label everything that's in here. So this one has a label because the closed-in circle here says there's an electrical connection. It's like a tiny wire around it at that point. If it's an open circle like this, that means that it's an inverter. It takes a positive. It's not a not operator. So this one's labeled with carry. This one is labeled with Y. This one is labeled with X. You may or may not see the little hop in the circuit here. It's hard to draw, so it depends on the program I'm using to draw things. If it doesn't have the black filled-in circle, they're not connected. So if they cross, they're not connected. So what we do is we provide names for those lines that are internal that have no other label. And we do that so that we can use them in the formulas that we're creating. So the other thing is our facts. Our facts, we don't have to do facts for the entire circuit. We do a fact for a gate. And then what we do is we allow the labels, the names that are used for the variables to indicate which gate we're talking about. So I don't have to have AND gate 1, AND gate 2, AND gate 25. I can have one AND gate. AND gates always work the same way, and that's what my facts do, is they say, given 2 inputs, I'm always going to have 1 output, and it's always going to function the same way. So my AND gate here is always the same. If I have 2 zeros in, I get a 0 out, a 0 and 1 in, I get a 0 out, a 1 and a 0 in, I get a 0 out, and then if I have 2 1s in, I get a 1 out. So it's always the same. So to identify a specific gate, all I do is I look at the names of the variables that are in here, and I relate them to where I'm at in my diagram. That will allow me to create an expression for that entire big diagram that I've given you. By labeling, these are labels that you can create on your own, given the diagram, and you can determine how you want to do things there. All right.
Question for you. Is there a reason yours is, the one up on the screen is different than the one that's in the actual in Canva? It's the exact opposite.
The one in Canvas has an N here. NAND.
Gotcha.
So you invert the output. Yeah. The types of circuits that we normally have are AND or not, XOR, NAND, and NOR. Where I have an AND where the output has a circle on it. See if I can get my pen to work here. This would be an and this would be a NAND. The circle on the output means it's knotted. The output is the inverse of what you would expect. So this would be an AND. This is an AND. And the only other one that we do this to, and I can't draw these quite as well, the curves for whatever reason just don't work as well with my hand. My hand doesn't work that well anyway. I'm not a good artist. I have an OR or a NOR. So all that means is I'm inverting the output. So in Canvas, for the example, I gave you the knotted ones because I didn't want to just give you the table. But this is a truth table. If you look at the rows here, each one of these is an element of the truth table, a row from the truth table. So if I draw red doesn't erase very well.
And they haven't given me anything to clean the board with. I'll have to use the black. The black erases. So my truth table for and, and of course I threw all of them over here. So for an and, I have 0, 0, 0, 1, 1, 0, 1, 1. This would be my X and my Y input. And since we're doing Boolean algebra, I'll use a Boolean algebra and the dot in between some Y. 0, 0, there's a 0, there's 0, 0, 0, 1. So I can take this directly. These are the values that I pull into my gate here. I have a 0 at the first one's a 0, the second one, the Y is a 0, and the output, or the operation result is a 0. Row by row, and that gives me the way that my gate operates. And then my circuit, I could have X, Y, Z, this would be F. I would label these T1, T2, or whatever names you want to give them, just temporary stuff. So I can combine these, and I'd say my circuit is going to be X, Y, Z, and F. And inside here, I'm going to have, well, I've got my and X, Y, T1. I've got my or Y, not looking at it, I'm just writing, Y, Z, T2, comma, and then I've got another and over here I'll have T1, T2, and my output. So all I do is I just draw gate by gate. I do this gate, and then I go. So a little tedious, but if you do an and or not, you've got 4 lines for the and, 4 lines for the or, 2 lines for the not, so that's 10 lines. Your circuit, you can do 1 gate per line, you can do a whole bunch of them. Please don't go beyond 70, or pardon me, 80 characters per line. It wraps when you print it out. If I have to scroll over to look at it, it's kind of a painful thing. You will dock points throughout the semester if you are egregiously exceeding 80 characters per line. And believe me, when people get into Java and C++ and they have an editor that allows them to enter, I think the longest line I've had so far is about 270, 280 characters. And even with font really, really small and a big window, I can't see what's on the end of the line. So I count off for that. The 80. Why 80? If you print in portrait mode, you get about 80 characters and 65 lines per page. 80 columns, 65 lines down. That's about it. So if you're looking at a printout of a program, anything beyond 80 lines is going to come down to the next line and it won't be indented. So now all the careful indentation you did in order to make sure that you'd be able to follow your code, it's all gone. So you get stuff interspersed. It's just I am imposing a
programming standard here. Now, I'm allowing you to program in any language, but you must limit yourself to 80 columns or less per line, and you have to have comments. Those are probably the two biggest things. I've had people in this class that turned in perfect programs all semester long and never put a comment in a code. Never. I even said, please put in comments, because the best grade you'll get on all of your programming assignments, if they're perfect, is 85%. So you're throwing away 15% of your programming score, which is about 4.5, 5, about 6% of your grade. So if you can do that and still get an A, you're doing really well. So, it's not worth it to throw it away. It's such an easy thing to add in a comment every now and then and say, these next lines do this, or these are the facts for an AND gate, facts for an OR gate, facts for a. The other thing to be careful of, and I put this in the assignment, is I don't remember which one it is. I think it's the and in the or the and and the not. But using that as the name of the rule can cause some issues because there's a built-in rule there. So just go with my and, or use your initial. Mine would be hand, or, and hanat. Whatever you want to do, just make it a unique name that won't be a built-in function in the language, and life will be good. Questions? All right, the rest of the class, I took 2 minutes from you last time. I'll give you 15 this time. That's the last thing that I have to present. I'll stick around for questions if you want to ask any questions, anything about homeworks programs. The GATE program, program 2, is the last prologue program we will be doing. So when we get to the next one, we're going to be using bit strings, or basically integers. I'm going to use an integer. I'm going to manipulate the bits in that integer to tell me whether or not something is in a set. Everything must be an integer, not an array of integers, not a set of integers, a single individual integer, and we're going to look at the bits inside there. So the homework I've got for that one, I give you code that will print out the bit representation of an integer. You send in an integer, it'll print it out in ones and zeros. So you can send it positive numbers, negative numbers, whatever you want. It'll print out the bit representation. And that's to show you how to get to the individual bits within the integer. So that's a heads up, but we don't look at that for another week or so. So if you don't have any questions, you're free to go. Enjoy a little extra time. Go get an energy drink to wake up for your next class, or some coffee. Starbucks is here, or hot cocoa. It was cool this morning. Whatever you feel like doing. Or stay here and look at the cherry blossoms over the pond somewhere. I don't remember where this is. So I'll upload the slides without annotations, and then for the ones that I've actually written on, I'd make a PDF and I'll upload the PDF as well. But I didn't write on it too much because my pen is not cooperating very well. Yeah. Have a good one. Thank you.
Thank you.
I just wanted to get hold of my Mac and getting this program run on. I don't know. I've installed the prologue, but I guess I should go to terminal. I've read the instructions, but I was still unable to run this. Can you help me with that?
Okay, I'm not really a Mac person, but I can try. Oh, no, please, you said. I'll kneel here and. Oh, SWITL. So it comes up with a prompt. At this point, we can type.
So how do I determine the file which I want to have?
Okay, I think it's consult. And the name of the file? Period. Syntax error, operator inspected, and that's what I got in when I ran it as well. So there's actually an error in the program. Unfortunately, right now it's not there. Bit? No? Q is kind of thing. That's function. No wonder. Okay. So control C will get us out of the input segment here. So we can actually exit. And then with the
The key things here are usually periods at the end, capitalize somewhere. Notice this one before you have here, and this, and here. Yeah, it would just be something like. Probably a good thing to get into would be siblings. And so that way, it's telling you why we do this. So, yeah, you shouldn't make these two different rules because that will cause issues because they both are siblings. When they have the same form, it will always be the first one that will be the second one. So, what I planned with the homework was that you would first do the first one and find out that Joe is her own sibling. And he's like, that's not the way it's supposed to be. It's supposed to be like this, where no one's their own sibling. So that one works. This one, it's the same rule, but it's not. It didn't add anything. We actually changed it to keep from having something wrong. And for sister, oops. And actually, we could do HW1 after that. And if you consult it, so that it should actually load a bit quick.
The first one to know the
If you don't, well, it should load it should load when you type in the file name afterwards. I'm not saying that it did, but we can try. So it did load. If you put the underscore in on it, or sister or sister out?
sister.
So, to consult another one at this point, for example, we did consult. Well, key one, so that was the problem. Period. Might keep forgetting the period. This one's saying that there's a syntax error, which is make sure it's not a consult statement. So it's saying that there's actually an error within the file. So you have a P1 PL. And so it's got. So it was pulled in, but it was, this part down here, you got route with two different structures. And it will try and work that, but the problem you have is that we're not building visibility and other stuff before we try and make the call. And that's gonna cause issues. So what I'd recommend is similar to what we did at the startup class with the Pony Express, where all you do is you just build a very simple route, the destination of stops. If there is a flight, stops is 0. And if there's a route, flight, another route, a recursive route, so something similar to this. Let me just say, if there's to be, that exists if there's a flight from A to B. Oh, I need stops in here too. If there's a flight from A to B in 0. That means there's a direct flight.
Yeah.
Flying from Salt Lake to Houston, I'm not stopping in Denver on the way. So that's what stops is, layovers or stops. And then the other part would be if there's a flight from A to C and a route from C to B with then it will be true that I've got a comment here and I'm out of room, so I'm just going to put it on the next line. That stops is layovers plus 1. That will do the simple count for us. If I want to add output, just as I did in the other one, then what I would do is I would insert in here and I'd just add right. Like a space and right. Well, what city am I stopping in? So do it right. And inside here, say, well, C is the place I'm stopping. And that would print out the name of the value of C that makes this true. So that way I don't have to try and build a list and then print the list out separately. But quite a bit simpler than what you had, and fewer things to look up.
This is quite simple. Thank you. One more question. Like, do you remember last week we had new 3 boys in the class? Did they join our Discord or?
They did not join today on Discord, I don't think. I looked once or twice, I don't think anybody joined, but I also record the lecture, so.
Yeah.